Hello to everyone. We're dealing now with the last part of probabilities chapter, which deals with random variable and probability distribution. So let's show and display the general frame of this part of the chapter. The purpose of discrete probability distribution corresponds to a random experiment that leads to a sample space omega, that is the set of all the possible results of our experiment. So that's not new for you at this point. But we have to consider a special situation where inside omega there are some different possible events like this event A or B or C or D. So that could occur in many possible situations. Even though we don't define events, we can define the sample space elements, okay, that are single outcomes that could be considered as events. So the most important for us is to consider that a random experiment could lead to some kind of result or some other kind or some other kind and so on. Well, this sentence, omega is partitioned in events, is just meant to say that each event will be associated with a value. So that is new in this chapter. Okay, we didn't talk about this kind of thing earlier. Each event has to be associated with a value. For instance, the event A is associated to 8. That means if you perform the random experiment and fall into A, you will be awarded 8 points or 8 euros, okay, if we're talking about money. For B, it will be, for example, 5. For C, let's put 2 points, and for D, no point, okay, 0 points. So you've got a new list that is a list of value, and in mathematics, a list of value is named a variable. And it can be denoted x, okay, this is the simplest way to denote a variable, x, like in a function chapter. This variable can be forecast, or one of its values can't be forecast. Each value gets a probability to occur, which is the probability of the corresponding event. So it's not a simple variable, it's a random variable. 8520 is a random variable. Okay. Next, you can establish a table and fill this table with the values of x, 8520, and below the values of the probability of each value. And then, by doing that, you obtain what is called the probability distribution of x. This is just this simple table. So, you know some special probability distributions, like the binomial distribution. Maybe you don't know about the hypergeometric distribution. So there are several discrete probability distributions that correspond to a given kind of example. In this slide, I'm introducing in a global sense the notion of probability distribution. When it doesn't correspond to a special case, you have to build and fill this kind of table in order to give the probability distribution of a variable. When it will be binomial, for example, you will be able to only mention the parameters of the binomial law, and you won't be obliged, you won't have to create this table. Okay? The simple fact to know the parameters of a binomial law is enough to know afterwards every possible value of probability of every event. So this general introduction is just a frame, okay, with a little vocabulary. By seeing that, you can admit that this kind of table really looks like tables coming from statistics, where we put values of some variable and below frequencies that can be expressed in the number of individuals or in a percentage of the total. Given that, you are able to use formulas that come from statistics as the mean, the average value. That is called in probability the expectation or expected value. The expectation corresponds to the formula sum of p sub y x sub y. That means from this table, p of A times 8 plus p of B times 5 plus p of C times 2 plus p of D times 0. That is exactly the way that we can calculate a mean in statistics by the mean of the formula sum of f sub y x sub y, the frequencies multiplied by the values. Okay, so we have to explain it a little further and so as to you to understand this special case inside a probability chapter. Okay, these are not statistics, these are probabilities. So the next slide will be here to explain you. And we were able in statistics to calculate a variance and a standard deviation. A variance corresponds to the formula sum of pyxy squared minus the mean of x itself squared. So this corresponds exactly to the formula of a variance in statistics. Okay, you will be able to compare both formulas, and you will see that indeed these are exactly the same formulas. And of course, in the next slide, we have to explain why it will be important for us to calculate a variance in probabilities. So before performing an exercise, let's have a closer look at the meaning of a probability. So I'm reading with you at this point, saying that the probability of an event A is 0.3, is saying that its chances to occur are 30% as an experiment is going to be performed once. Okay, so let's analyze this first sentence. You are about to try a game, a random game, and you know that some event has 30% chances to occur. Does it say anything to you about your chance to succeed the next time you will try? In fact, no. And you can imagine a heads or tails game with a coin that you can toss, okay? And when the coin falls down, the result is head or tail with 50% chances for each. But it won't help you to know what will happen next time. Next time you toss the coin, you won't know at all which side will fall down. So a probability is not here to help you to forecast what is going to happen next time. So let's read the second sentence. Ideally, on reproducing this experiment several times, the event A will be realized with a frequency of 30%. So you can see here that we're talking about several times and maybe a large number of times, okay? A large number of attempts of your experiment, or you can say of trials, okay? What does this ideally mean? It's an average. A probability is an average. on average, you can expect that the event A will be realized in 30% cases. When tossing your coin, you can say that in or after a large number of toss, ideally you have to get 50% heads and 50% tails. Okay, maybe the reality will not be exactly corresponding to this 50%, but the reality won't be far from this result. It will be very close to this result, and it will be the more close to this result than the number of attempts is big. So a probability tells you about an ideal situation after a large number of trials of your experiment. So let's sum up by this sentence. It is found and proved that the greater the number of attempts is, the closer the realization frequency of an event is to its theoretical probability. So the realization frequency is the percentage of occurrence of the event A that is real, okay? That's your real percentage. And as the number of attempts tends to infinity, this realization frequency tends to the probability. If an event has 30% chances to occur, let's realize your experiment a large number of times, and you will see that the realization frequency, the concrete realization frequency, will be close to 30%. This result is called weak law of large numbers. So, of course, there are possible variations around this theoretical frequency of 30%. Okay, and maybe the next attempt will make the realization frequency evaluate to be a little further from this 30%. But next time, or the next after, you will see the realization frequency get closer to 30%, and so on. And as the number tends to infinity, the realization frequency tends to 30%. So the random follows rules, and that's not intuitive as a result. The random of each experiment, one after the other, follows rules when you're talking about a large number of trials. Of course, we've got to have a closer look at that, and let's consider a game where you can fall in an event A or in its contrary, which I'm calling B here, but which could have been noted A bar, of course. The first situation has a probability of 30%, and so the second one has a probability of 70%. And I'm associating gains, why not in euros here, the variable x. If you fall into A, you will earn 10 euros, and if you fall into B, you will lose 5 euros. Okay, so let's make a simulation of what could occur with a large number of attempts. And I considered 137 attempts. Why not? The blue curve gives you the real number, cumulative number of realizations of the event A through time and through the number of trials. Ideally, I would have to follow the red line. The red line has an expression that is y equals 0.3x. That means that y at each time, at each point, equals 30% of x. So, for example, if x equals 20, On the red line, y equals 6. 30% of 20. If x equals 100, y equals 30. Okay, after 100 attempts, my ideal realization of A is 30. Okay, I'm expecting A to be realized 30 times in 100 trials, and so on. The reality presents fluctuation, variations around this ideal situation. In some situations, sometimes the real number of realizations of A is bigger than expected. And in other situations, this number is lower than expected, and so on. But the reality turns around this ideal line. So that is a cumulative graph. What if we divide the number of realizations of A by the number of trials for each point? It leads to the second graph that is displayed here, that, where you can see, firstly, with a little number of attempts, that you can't forecast anything on what could occur on average. Okay, the percentage of realization of A can be far from 30%, that is here. 30%, this red line, can be outspread here, or the reality can be very far below. With this simulation, I was lucky with my event A on the beginning, but as the number of trials tends to be higher and higher, the reality on average as a percentage of realization of A tends to 30%. Okay, and that is a graph built with the first one, okay, taking the same values but dividing them, each one of them, by its number of trials. Okay, and you can see that, yes, indeed, according to the fact that you realize your experiments 60 times or 80 or 100 or 120, the frequency of realization, this realization frequency, tends to the theoretical probability of 30%. So, in a next slide, we will have a look at an overview of what could occur to the gains in euros in our game. So let's take back our first simulation, but now let's calculate gains in euros. When A is realized, you win 10 euros. When B is realized, you lose 5 euros. The first little graph on the right shows you the cumulative gain in euros through the trials. Okay, and you can see that, yes, A is more realized than expected at the beginning, so you are winning euros. Okay, but next you can see that the realization of B tends to be bigger, and the both percentages of realizations tend to the both numbers that are here, the probabilities, 30%, 70%. This way, your real gain will come under zero, and you will see that you are losing money. And the more you play, the more it appears that you tend to lose money. Next, if you divide each cumulative gain by the number of attempts, you got the average gain per game. Okay, this is the second graph, the big one, that tells you that on average, it seems that your gain tends to a given value that appears to be negative. You are under zero here. And our formulas will begin to appear. The expected value corresponds to this formula. E of x, expected value of the gain in euros, is the sum of p, y, x, y. So let's take the table and calculate the sum of p, y, x, y. 0.3 times 10 plus 0.7 times minus 5. The result is negative. It is negative 0.5. So let's display this negative 0.5 on the graph that has been built with average values, because E of x is an average value. It's here. And yes, you can see that your simulations, or my simulation, shows a gain that tends to negative 0.5 euros. Okay, after 100 trials, this value is very close to this number, negative 0.5. So it means that negative 0.5 multiplied by 100 gives you approximately your gain, your cumulated gain. And it's equal to negative 50 euros. You lost 50 euros. So let's go back to the first graph. After 100 trials, your real cumulated gain is, yes, indeed, approximately negative 50 euros. Okay? There are fluctuations around some ideal line that is not displayed here. What could be the ideal line? But, well, if the ideal average gain is to lose 50 cents each game, so you can draw a line on the first graph, which expression could be y equals negative 0.5x. Okay, so your gain y equals negative 0.5 times the number of trials. So let's draw this line, and yes, it appears that my simulation seems to try to follow this red line, okay? In fact, it doesn't try to follow it because there is no intention with the random, okay? But the random follows rules and laws. So let's go a little bit further and let's try to talk about the possible fluctuations of the reality around the ideal line. And that's the role of the variance. The variance corresponds to this formula, and the standard deviation is the square root of the variance. Once again, just as in statistics. So, by the way, what's the difference between statistics and probabilities? Well, statistics show you what happened in the past, and probabilities try to focus what could happen in the future. But with the same language, so the formulas will be the same. So a first simulation of gains could be this one. Let's display on the same graph a second simulation, okay, that is made again by random. Okay, another player could have obtained this kind of curve, and a third player could have obtained that. So this player is quite unlucky because this player always loses money. Okay, sometimes it wins money, but the cumulated gain is always negative. For a fourth player, this could be that in yellow, and for a fifth player and last one, this could be this green curve. Okay, you can't see maybe anything looking at this graph, but let's establish the graph of the average gain in euros through the trials. The blue curve corresponds exactly to the first blue curve by dividing each result by x, the number of trials. Okay, so you've got your average gain per game since the beginning. as in the previous slide. So you can see that this first player was lucky at the beginning. The average gain was big and positive, but the realization of the event B go to or make the result decrease little by little and go under 0. So let's have a look at the other players, the other simulations. The red one looks like that on average gain. The gray one is that. The yellow one is that, and the green one is that. So there were big differences between players, let's say between 0 and 20 trials. Maybe again, big differences between the 20th and the 40th trial. But through time, the results of every player begin to look like each other. Okay? If you divide these numbers by the number of trials, the results will look like each other. In fact, there exists confidence intervals to try to forecast what could happen for every possible player and every possible game. It's established that, or it's stated that, the center of such a confidence interval will be the number of trials multiplied by the expected gain. Okay? The average expected gain multiplied by the number of games will give you the average cumulated gain or cumulated gain. And to create a confidence interval around that, you have to add or subtract a second number that is calculated on a standard deviation. And that depends on the number of trials again. So it's been stated that, and I won't explain it here, it's been stating that the variance increases like the number of trials when you try something several times. The variance is proportional to the number of trials, but the standard deviation is the square root of the variance, and then the standard deviation, the overall standard deviation, is proportional to the single standard deviation and to the square root of the number of trials. So what does sigma of x mean here? Let's take a numerical example. Let's take a 95% confidence interval and let's build our interval for 100 trials. All these numbers give these calculations which lead to this result. So, what is the 6.874? This is sigma of x. What is that? It's a number of euros. It's a standard deviation, so it's an average deviation or average variation of your gain from one attempt to the other. If you are trying your experiment once, you got some gain. Next time, your gain will be the same or will be another. So there will be a difference or not between your gain and the next game. This difference, considering a large number of attempts, has an average. Okay, so it's the average variation. If you multiply it by the square root of number of trials, you've got the average variation of your cumulative gain. Then a coefficient appears that is denoted u here by the letter u. That depends on the normal law. So I will explain it to you better in the next chapter when we will talk about the normal law. But you're already used to use this kind of coefficients. If you want a 95% interval, you have to put on the standard deviation a coefficient, a multiplicative one, of 1.96. If you wish to establish a 99% confidence interval, you have to use the coefficient 2.58. Okay, that are classical coefficients, but for each percentage that you would have to consider, there exists some value for the coefficient u to be used. Okay, so its use is to enlarge the standard deviation in order to own more possible attempts. Okay, and if you want to own 95% of the possible simulations here, you have to put this coefficient that is close to 2. Okay, our result is negative 185 to 85. Let's put it on the graph. Okay, so it goes from here, negative 185 to here, 85. The center being negative 50. So exactly here. So that means that after 100 trials, 95% of the simulations will cross this line. So this segment, okay? And that means that 2.5% of the simulations will be higher and 2.5% will be lower. So it's a confidence interval in terms of prediction, okay? It tells you that you can make all the possible simulations that you want. 95% of them will cross this red line. Okay, so let's draw the previous line, which expression is y equals negative 0.5 times x. Okay, this is the center or the central ideal simulation. Each time you try, each time you lose 50 cents. So after 100 times, you lost 50 euros, and so on. So this is your central expectation of cumulated gain. But this confidence interval shows you a vertical prediction that tells you that the possible fluctuations of the reality are here, or 95% of the possible fluctuations. So we could have established a confidence interval for another value as 100. For example, for 80 trials, or 60, or 120, and so on. So if you want to draw every possible confidence interval, what would be the global shape of your intervals? Well, according to the fact that there is a square root of n here, this shape will be a parabolic shape. Okay, you will see a parabola appear here and here. Let's draw them. The two parabolas that correspond to every possible 95% confidence intervals are these ones. So it shows you that the more you try, the more the possible variability is big. The bigger the variability is. Okay? But I can assure you that this dotted line here on the top will be decreasing and rapidly decreasing with a slope that will follow the central line. The slope of each parabola tends to the slope of the central line. So, what appears on average on the second graph? If you have all of that, and if you divide all of that by the number of attempts, that is by n, what is the result? The result is the confidence interval for the expectation or for the real frequency, that will be e of x instead of n times e of x, and u sigma divided by square root of n instead of multiplied by square root of n. This time, the possible variability of the reality decreases as the number of attempts increases. That's why the possibilities and the variability tends to tighten as n increases. So this kind of interval leads to this calculation with the same example, the same numerical appliance. And of course, the result is the first one divided by 100 here. On the graph, this is a red line, that is this one. And I have to draw again the central expected line that is centered to negative 0.5. This time, the curves that can put a limit on these 95% confidence intervals present this shape. Okay, these are not hyperbolas, but they are close to hyperbolas and not parabolas here. So you can see that indeed the 95% of the simulations will be imprisoned inside these two lines, okay? And the more n's, or the bigger n is, the closer the two lines are, okay? And they both tend to the central line at the 8 minus 0.5. So let's calculate a last example with a far bigger value of n. Let's take 10,000 trials of our experiment. If you replace this time n by 10,000 instead of 100, the results are these ones. This time, your first interval in terms of cumulated gain is clearly negative from the beginning to the end. You have clearly no chance to win money after 10,000 trials. So you could say that you will never play this game 10,000 times, but you could be the organizer of this game. You could put it online, and maybe the players could be on the internet, and maybe you could have a lot of players. If you want to forecast what could happen for a lot of players, this confidence interval tells you that 95% is the probability that you, as an organizer, will win between 3,600 euros and 6,300 euros. That's a prediction of your gain at the organizer of the game. And on average, a player, each time he or she plays, will lose between 36 cents and 63 cents. So it's a good way to see how the possible gains, and not the ideal ones, okay, but the possible real gains will evaluate through the number of attempts. Okay, let's see the basics and this kind of intervals in two exercises that share the same statement. The exercise 31 presents us a lottery that is held. That could be online, okay, in order to be able to consider a large number of players, okay, online on a website. So 100 tickets are to be sold. Each time 100 tickets are available, whether they could be made of paper or not, okay? And you have to bet €1 to play, or you have to pay €1 to buy a ticket. One ticket is a €30 winner. Two are €50 winners, and 7 would make the buyer win €1. Okay, considering we want to purchase one ticket, so each player is allowed to play only once, X is the random variable of the net gain. So the net gain means that you have to subtract the €1 you expended, or you spent. Give the probability distribution of X. So you have to give the list of possible values of gain, and below their probabilities. Of course, you can win €29 with the €30 winner tickets, and your chance is 1 in 100. Okay, the fraction is 1 over 100, so 1%. You can win €14 with 2% probability. You can win nothing, so you will be refunded your euro here with 7% chances. And all the rest, the loser tickets, are 90. So you've got 90% chance to lose your euro that you spent. So that is the probability distribution of X. We just answered the question. Next question, if we were playing this lottery the same way many times, or if a large number of players play 1, 2, or 3 times, can we expect to be a long-term winner as a player? Okay, so can the set of players can expect to be a long-term winner? So I wanted to calculate the expectation after 1,000 attempts. And let's have a look at the calculation that appears. If you've got 1% chance to win €29, if you try this game 1,000 times, you can think or you can forecast to win 10 times. 10 on 1,000 is 1%. So you can expect to win 10 times €29. Besides, you can expect to win 20 times €14. You can expect to win 70 times nothing. And you can expect to lose 900 times €1. The result, unfortunately, is negative. It's negative €330. So that's an expectation, an ideal expectation, only based on the probabilities. As we've seen earlier, the reality can variate around this expected value of cumulated gain, of course. And our purpose is to establish the way that it can variate around this value. But this question is simple. If we're playing this lottery the same way many times, can we expect to be a long-term winner? Once you notice that your expectation is negative, then you can conclude that you can't expect to be a long-term winner. You will be, in long term, a loser in this game. And the organizer of the game will be the winner. That's all. Okay? So we can expect an average loss of 33 cents per attempt. And indeed, if we calculate the expected value, E of X, so the sum of P, Y, X, Y, we have to multiply this number by this one, this number by this one, and so on. The result will be negative 0.33. So even though this accurate result is not likely to occur, the law of large numbers tells us that the more we'll play this lottery, the closer our actual average gain will be to this average expected gain. One cannot expect to be a long-term winner. So to go a little bit further, we've got exercise 32 that goes back to the data of exercise 31. Calculate the expected value and the standard deviation with the data of exercise 31 and comment. So at this point, I have to explain you that you are not obliged to calculate by hand these parameters, expected value and standard deviation. Since this is exactly the same kind of table as in statistics, you can use the stat mode of your calculator, enter the values of x in the first list, the values of p as frequencies in the second list, and ask your calculator for results in one variable statistics. Okay, the variable being in the first list and the frequencies in the second one. Your calculator will give you results directly. The expectation that is noted x bar on the calculator is negative 0.33. And the standard deviation is 3.622 approximately. So I hope you understood well the meaning of the first one. The meaning of the second one has to be explained again. Okay, on average, the possible variation of your gain from one game to the other, to the following, is plus or minus 3.6 euros. Okay, so how could we comment these values by examples? Let's go back to the formulas of confidence intervals. And let's talk about the most important, that is sigma of x divided by the square root of n, number of trials. So this means that in n attempts with n big enough, the actual average gain is a random variable, normally distributed, centered on negative 0.33, with a standard deviation of this fraction. For instance, in 10,000 attempts, the standard deviation of the possible average gain is approximately 0.036 euros. Okay, so this value divided by the square root of 10,000, that equals 100, okay? So instead of 3.6 euros of standard deviation, in 10,000 attempts, you've got a 3.6 cents of standard deviation. So of possible and probable distribution or deviation around this center average gain per game. So the fact that this distribution is normal implies, for instance, that, and we will explain these sentences, of course, there are 68.3% chance that the actual average gain would be between this number and this one. So this is the standard and basic formula of a confidence interval that tells you that you've got chances to be between, so that means the reality has chances to be between this central expected value minus something depending on the standard deviation, and this central expected value plus the same standard deviation. But if you are subtracting or adding only one standard deviation, that is the case here, you are creating a confidence interval with a coefficient u that equals 1. And by doing that, your result is a 68.3% confidence interval. So there is 68.3% chances that the reality will be inside this interval. So your real average gain. With negative values, you can say a real average loss. Okay, so if you multiply these values by the number of trials, 10,000, you obtain your cumulative loss and not gain, So you've got 68% chance that your loss will be between 2,900 euros and 3,600 euros. If you want to use 2 standard deviations instead of 1, you will create bigger confidence interval, okay? Its size will be multiplied by 2. So now it will go from negative 0.4 to negative 0.258 instead of the former one. But by taking 2 standard deviations, you improve your confidence level, of course, and it will be improved from 68% to 95.4%. But if you want to fix your confidence level at exactly 95%, you have to choose not exactly 2 standard deviations, but 1.96. You will be, or you will see this coefficient appear again. If you take 1.96, you will be, or make this number decrease a little bit to 95%. Okay, and so on. As I told you earlier, each percentage is associated to a certain coefficient u. If u equals 1, you've got 68% of confidence level. If u equals 2, 95.4%. If u equals 1.96, 95%. If u equals 2.58, 99%, and so on. Okay, so you can comment these results by being more concrete and talk about what could be the reality if you consider a certain number of attempts. Okay, and it will make your explanations more clear than the simple fact to give these results. So you will have to be able to do such kind of things, even not as precisely. Okay, you will have to be able to do all of that in the future test, for example. Okay, thank you. We'll see and talk about all these explanations and the following exercises in next session, and thanks to a next video. So don't hesitate to comment below this video, of course. Thank you all, and see you next time for a new video. Bye.